So I would like to welcome everyone to come to our first colloquium of winter 2020. It's really unfortunate because that this is remote, because I was really looking forward to see Carlos in person in many years, I feel now, after all the pandemic. But I'm also glad to have him talk at Queen's on IceCube related even in this remote manner. So to begin, let us acknowledge that Queens is situated on traditional Anishinaabe and Haudenosaunee territory, and we are grateful to be able to live, learn, and play on this lands. And as I just was chatting with Carlos, I am teaching. Oh, Carlos, can I share screen just for a second?
Yeah, of course.
Thank you. I'm sorry. Since I just wanted to share this because I'm teaching Astro 102 right now, and I was searching for it and I found this brilliant sky map. It's Msw sky map, and also you can see that the Greek usual constellation behind, but also this is original the Anishinaabe people's, Msw people's actually sky map. And I also find this 2008 publication listing basically all the Aboriginal Canadian sky lore related with the Big Dipper. So as you can imagine, there's a lot of different cultural story, even just on the Big Dipper itself. And the sky you just seen was actually the fisher. And there's a whole story about even including this small, tiny arrow. So it was a really nice learn. And I think this is also kind of finding power potentially between the Aboriginal people and later comer as us, because there's something that we can talk together. So I thought to share that. Now you can feel free, Carlos, to share your screen again. Thank you. So Carlos is right now in Harvard University. He is my colleague working in the IceCube, and he is really, really brilliant physicist. I always envy of his insight on the statistical analysis and theoretical insight. So I'm really glad to have him here to share this about the searching for the new friends with IceCube. I'm pretty sure you will enjoy the presentation together with me. With that, Carlos, would you mind leading from here?
Yeah, thank you very much, Nahi, for a wonderful introduction and that story. I really like the constellation you showed. That's really cool, and maybe that's a good way to segue into this talk, which is trying to find new particles, new manifestations of nature with neutrinos. So neutrinos have other new, as I call them, friends here, and I want to spend these first minutes of this talk giving you a big picture of what I'm going to try to do and show you in this presentation. And that's going to revolve around two questions. And one of these questions related to how does the universe look in neutrinos, which is what Nahi works on together with the IceCube Observatory. And then the other question is the question of how do high neutrinos behave? And these are actually complementary questions. We're going to learn both about the universe and about the neutrinos at the same time. And these fake glass panels here, they show you three different ways in which we can see the universe. We can see it with neutrinos, we can see it with gravitational waves in the middle panel, and with gamma rays observations or light in general. So by looking at the universe with neutrinos, on general with natural neutrino sources, we have learned a bunch of things about neutrinos. And the spirit of this talk is to keep learning about neutrinos by examining them. This is an image of the sun taken by the Super Kamiokande experiment in 1998. This is an image of the sun in neutrinos. And this sort of foretells an interesting story, which is the fact that when we saw the sun in neutrinos, there was a significant disagreement between expectations and observations. This actually led to something known as the neutrino problem, which eventually was actually solved due to measurements actually made in Canada in the Snow Lab laboratory. But this story, I think, is going to hopefully repeat itself as we examine other natural neutrino sources and new neutrinos in new regimes to see if there is other surprises as we saw when we saw the sun in neutrinos. So what is the underlying framework that I'm going to be talking about? When I say about surprises, I need to have a baseline prediction, and that is going to be the standard model of particle physics. And the standard model of particle physics is a very successful theory that describes the fundamental interactions between what we know as fundamental particles, which are particles that don't have components and are in point-like particles. It's a model that has been tested in different settings, in different energy ranges, and with different experiments. And we have found that in a observable, it matches expectations very well. So it's a very predictive model, it's very well tested. But I'm going to argue that for a fundamental theory, it's actually kind of a complicated model. Here I present you all of the standard model particles. And so they are grouped here by their type. So the first two rows are particles, then the third and fourth row are antiparticles, and the bottommost are the bosons that are going to mediate the forces among particles. So you see the quarks that are inside the proton and neutrons. Then you have the leptons, and there's the neutrino, which is going to be our point of attention. And then the antiparticles are just replicated. And you can see that there is a lot of structure in this arrangement of particles. We have within the standard model, we have group particles in certain ways, given their properties. Some of the structure of this model is actually not explained. For example, the flavor structure that we see in the standard model. This is not the first time that, as humanity, we face this sort of problem. A couple of years ago now was the 100-year anniversary of the periodic table. And here is the periodic table. We know that it was made by organizing elements by common features. And in some sense, the standard model has done that as well. But we know that the periodic table, of course, is not a random arrangement of elements. The elements are arranged in this particular way because of the way the electrons are arranged on atoms. And so a more fundamental theory, which in this case is quantum mechanics, allows us to explain the patterns that we see in the elements. And so my hope is that in a similar fashion, there may be a more fundamental theory somewhere beyond the standard model that makes the standard model particle content manifest. There are other reasons why it's interesting to think about physics beyond the standard model, one of which is related to the fact that the universe has a large amount of it is unknown when it's comprised of dark matter and dark energy. So the standard model only accounts for about 5% of the observable universe. Another reason that is interesting to look at the standard model and is particular to this talk is the fact that in the standard model as originally composed, neutrinos were meant to be massless particles. However, we know now that neutrinos, and I will tell you how we know this in a little bit, the neutrinos actually do have masses. We do not know exactly how they acquire these masses, but so that's the point of that tells us that there may be an interesting direction to look for new physics as well. So in general, there is going to be a large number of questions that are related to the neutrino sector. For example, the matter-antimatter asymmetry could be studied in neutrinos. The question is why neutrinos are left-handed particles, if neutrinos interact with dark matter. I will tell you a little about some experimental results that are really strange later on and what those could mean for the neutrino sector. And the overall theme of this talk is that if neutrinos have done something weird, which is manifestly having mass from respecting to this massless, are they going to do something weird again? And so the theme of this talk is to think about we live in interesting times for neutrino physics. So the talk is then organized in four pieces. So first, I'm going to tell you about neutrinos. I'm going to tell you about IceCube. And then I'm going to give you 3 examples of how we can look for what I'm calling these new neutrino friends, these additional parts that the neutrinos may be talking to. And so I'm going to give you 3 examples. We're going to look for a new particle, so a new kind of neutrino, non-external neutrino. Then we're going to talk about new forces that the neutrinos may be connecting with dark matter. And then we're going to talk about new space-time symmetries. Okay, neutrinos and IceCube. So there are 3 very light neutrinos. The mass of the neutrinos is no more than 1/1,000,000th of the mass of the electrons. And neutrinos are produced in different ways. Neutrinos can be produced in anthropogenic sources or in natural sources. In this talk, we're going to use neutrinos of natural sources, but let me comment a little bit on different neutrino sources. The closest high intensity neutrino source for us is the sun. As I was showing you earlier in the picture by Super Kamiokande, the sun produces neutrinos in large amounts due to nuclear reactions inside the sun. There are also neutrinos that are produced in explosions of supernova, and those have been also observed. There are also neutrinos that are going to be produced in high energy processes, and those are the ones that IceCube sees, also like in Astrophysical Sources. There are going to be neutrinos that are going to be produced in the interaction of cosmic rays. Cosmic rays are charged particles that hit the Earth atmosphere. And when they hit the Earth atmosphere, they initiate a cascade of particles, and that produces neutrinos. So cosmic ray air shower production of neutrinos yields something known as atmospheric neutrinos. There are also neutrinos that are relics from the Big Bang, and those are of the order of 1 billion per cubic meter. That's the analogous of the CMB, but in neutrinos. There are also neutrino sources that are anthropogenic, and those are essentially going to be reactor neutrinos and accelerator neutrinos. In this talk, I'm not going to use those sources. I'm going to use neutrinos that are produced in cosmic ray air showers, and I'm going to use neutrinos that come from extraterrestrial objects. Neutrinos all interact via the weak force, which means that neutrino interactions are rare. So how rare is that? So in particle physics, we like to quantify the chances of interacting by something known as the cross section. So that's sort of like an idea of the geometrical area of the collision that between two different particles. So if I have a neutrino that has an energy of typical solar present in the solar core, the probability that that interacts with a proton is quantified to be of the order of 10 to the minus 43. That's this cross-section area. Whereas the cross-section area of a proton-proton collision is of the order of 10 to the minus 24. That means that it's about 10 to the 20 times more likely a proton to interact than a neutrino. And that means that if I have a neutrino produced by the sun, it has a good chance of traveling around 200 Earths before it interacts at all. However, this statement is going to depend on the energy. As you will see later, this can change a little bit. So how do we describe interactions in particle physics? We describe it by the exchange of particles. And so we use these so-called Feynman diagrams, and here is a sketch one for you. The horizontal axis is thought as the time, and the vertical axis is thought as position. And what you see here is a scattering of two particles. You have a neutrino, you have a d quark, and those scatter, and when they scatter, they exchange a C boson, which exchanges momenta between these two particles. And when they come out, you get your neutrino and your d quark. So this is much like a billiard ball kind of scattering that you will think about. However, neutrinos not only have this billiard ball scattering, which we call a neutral current scattering because the C boson has no electric charge. They also have something known as a charge current scattering. In a charge current scattering, neutrinos actually change identity. So an electron neutrino in this case is going to come in and it's going to hit a d quark, and it's going to exchange a W boson, and in doing so, it's going to produce an electron. A mu neutrino is going to be such that when it actually has this charge current interaction, it produces a mu. And a tau neutrino is one that produces a tau. So we organize the neutrinos, or we label the neutrinos by their flavor of the outgoing particle when they have a charge current exchange. And that's what defines what we know as a neutrino flavor. In the standard model, the neutrino flavor state and the associated charged lepton that comes out of the interaction are intimately related and built into the structure of the standard model. So one thing that the standard model predicts is that the neutrinos should not change flavor, but we have discovered through measuring natural and anthropogenic sources that neutrinos do change flavor. So how does this work? Well, you have a source of neutrino flavor. In this little diagram on the bottom is going to be a mu neutrino source. And I put some detector at some distance that can measure, let's say, muons, and I can measure electrons. So if I put it very close to a mu neutrino source, I see essentially only muons. But if I move my source farther away from the source, I'm going to discover that the number of muons that I observe is going to go down, but I start seeing electrons. That means that the mu neutrinos have converted into electron neutrinos. But what happens is that this phenomenon is actually periodic. If I move my source farther away, it's I start seeing the electrons again disappearing and the muons going back to the initial rate. And this will go on and on. The way we can model in this particular case is actually quite simple. It turns out that the frequency of the oscillations, so how fast they go in distance, is going to depend on the neutrino energy, and it's going to depend on the mass square difference, so the difference between the masses of the different neutrinos involves. The amount of conversion is actually a parameter that's given by nature, and it's known as the mixing angle. In the standard paradigm of neutrino physics, we understand this phenomenon by saying that there are 3 neutrino mass states, which we know as nu1, nu2, and nu3. And each of these mass states is composed of different flavor states, as shown in the cartoon on the left. So for example, nu1 is mostly nu-e with a smaller nu-mu and nu-tau component. And nu3 is the one that has the least amount of electron and larger amount of mu and nu-tau. We know the composition of each of the mass states fairly well. We also know that nu2 is more massive than nu1, and we know more or less the difference between the masses of those two. We know the difference in masses between nu1 and nu2 and nu3, but we do not know if nu3 is heavier or lighter than nu1 and nu2. And this is known as the neutrino ordering problem. In this setup, it's also possible to have a difference between the oscillation patterns in neutrinos and antineutrinos, and that is quantified by a CP violating phase. And so that's to be determined in next generation experiments. But this picture here, this slide essentially summarizes the neutrino oscillation, what we know about neutrinos oscillation phenomena right now. So neutrino oscillation is a quantum mechanical phenomenon. It's essentially a two or three level system that is where the production and detection are not the same as the propagation states. So it can be modeled by the Hamiltonian that you see here, and that Hamiltonian is going to depend on the neutrino energy here, E. It's going to depend on the mass square differences, so the difference in masses between these states is going to dictate the frequency of these oscillations, and it's going to depend on the composition of the mass states in terms of these flavor states, which is this matrix here, U. And what's going to happen is that neutrinos are going to evolve according to this Hamiltonian, are going to be produced in a particular flavor state, and then are going to evolve in this according to this Hamiltonian. So the fact that when neutrinos are changing flavors, that means that they have to have intrinsically a feeling of, or they have an internal clock, let's say, that tells them that it's time to change flavor. This implies that they must have mass, because if a neutrino will be massless, it cannot have a sense of time. This is not the only thing that you can do with this Hamiltonian. It's also possible that the neutrino flavor transitions are modified in the presence of interactions of different particles. So for example, in the case of the sun is full with electrons, and those electrons can interact with neutrinos, as shown in this diagram on the right. And that interaction is going to modify the oscillatory pattern. This is actually quite important to understand the transformation of neutrinos in the sun, and is known as the Msw effect. So in this talk, we're going to be looking for effects that relate to neutrino flavor morphing. Flavor morphing can be due to the natural oscillatory features of the neutrinos as they go from one state to the other due to their mass differences, or could be induced due to external forces, like in the case of the sun, a matter that is just full of electrons. And we're going to look for strange flavor morphings as signs of new physics. And that will hopefully tell us about new neutrino forces. So we're going to use neutrinos in IceCube. So this is the IceCube computing center. This is actually what you will find if you go to the South Pole, close to the actual geographical South Pole. So where is that? So IceCube experiment is very close to the Antarctic to the geography as a pole in Antarctica, I tried to make this diagram as close to what I could to scale. So you can see the relative size of the Antarctic continent to Canada. Of course, there's a geometrical distortion because of sphere to plane, but it tells you that Antarctica and Canada are both quite large places, and I hope I got Queens more or less right. So if you were to go from Queens to Antarctica, like this student here, you'll find the South Pole marker, and therein is the actual geographical South Pole, and the IceCube laboratory that I showed you some slides before. But that is actually not the IceCube experiment. The heart of the IceCube experiment is actually buried inside of the Antarctic glacier. And so here is a diagram of that. So the top little building you see on the top was the building I was showing you above prior, the IceCube laboratory. And this is in the top of the Antarctic glacier that has about 2.5 kilometers in height. So 1.5 kilometers deep into the glacier, we have instrumented an array of light sensors that are organized in what we call strings. And each string is going to contain 60 light sensors, and they're going to be separated about 70 meters vertically within each of these strings. Additionally, the strings are going to be separated about 125 meters horizontally between strings. Together, they instrument approximately 1 cubic kilometer of very clear Antarctic ice. So that implies about 1 gigaton of target material for neutrinos to interact. So these light sensors are known as digital optical modules or DOMs, and they are PMTs that have their own data acquisition system that are encapsulated in a pressure-resistant vessel. And like I was saying, they are arranged in these strings, making a regular grid or approximately regular grids. And they have the capacity to digitalize the data in the actual DOM and also communicate to the nearby sensors in order to sequence in signatures. So what can we do with this? These sensors are designed to observe chunk of light produced by charged particles. So for example, a mu neutrino comes through the Earth and it can interact in the ice or the rock below the detector. And when it does so, it can produce a muon. The muon is going to be above Cherenkov threshold in our case, so it's going to be a high energy muon, and it's going to meet Cherenkov light. Cherenkov light is emitted with this particular cone shape. So what you can do is you can see the time of arrival of the light, and with that, you can figure out the muon direction. So let me show you how this looks in our Monte Carlo. This is a Monte Carlo of an IceCube event. So here, these vertical lines are the strings of the detector. And then you can see these balloons. These balloons correspond to the different, correspond to sensors, so to light sensors that have been stroked by light. The bigger the balloon, it means that more Cherenkov photons hit that sensor. And the smaller the balloon, the less amount of photons hit that particular sensor. You will also notice that they are colored. And the color here indicates time, where red means earlier times and blue means later times. This means that what happens here is that the muon entered a detector from the left side of this picture, went about 1 kilometer through and exit on the right. So you can imagine that by looking at the time and spatial position of these hits in these detectors, you can reconstruct the direction. However, you can also reconstruct the energy, because what happens is that these are very high energy muons, and for muons that are above a TeV, the energy loss of muons, so how the rate of energy loss by a muon is proportional to the muon momenta. So by measuring the rate in which the muon loses energy as it goes through the ice, I can actually figure out its energy, and from there infer the neutrino energy. These events are really big. There is no way to put this in the screen, but here I show you one of these events in terms of, this is actually a big park in Boston, but you can see how that compares to buildings around it. This is actually kilometer scale interactions that we're seeing. So as I was saying earlier, neutrinos have 3 types of interactions. They have, that depends on the flavor. So muon neutrinos will produce muons, and those we can see when they interact in the detector or around it. Electron neutrinos are going to produce electrons. Those we can see when the electrons, when interaction happens inside of the detector instrumented volume or partially around it. And then tau neutrinos are going to produce taus, and those we can see when the interaction is inside of the detector, or rather we can identify them as such when interaction inside the detector. These Feynman diagrams are going to translate to observables in our detector. These are observables that they translate to, so they produce different morphological shapes on the light that we observed. Charged current muon neutrino events that produces high energy muons produce very long tracks of light, which you can see on the top, on the leftmost panel. And for those, we have a better than 1 degree angular resolution, so we can use those to, for example, look at neutrino sources, astrophysical neutrino sources. The NR resolution is poor, mostly because it's not contained within the detector volume. Neutral current interactions of all flavors and charged current electron interactions produce electromagnetic or harmonic cascades of particles, which in turn produce approximately symmetric emissions of light. The energy deposited in the detector can be estimated within or measured with an error of about 15%. And in these cases, you can imagine it's much harder to figure out the direction of this blob than the case of the muon, and the angular resolution is about 10 degrees at 100 degrees. Tau neutrinos produce special signatures. So when you have a tau neutrino, it can interact, in this case, in the blob in red, and it can produce a very boosted tau particle. To give you a sense of scale, if I have a 1 PeV tau, that is going to travel approximately 50 meters in the ice on average. And then that tau that's produced is going to decay further along in the green blob. This produces something known as a double cascade signature, which is a smoking gun signature of a tau neutrino, and we can see those above 100 TeV approximately. Tau neutrinos are very special and are very difficult to see. They are the least of, let's say, studied neutrinos in the in neutrino physics, and there's a good reason for that. And let me explain you with this plot here. The vertical axis here, the horizontal axis here is the neutrino energy, and the vertical axis here is the ratio of the cross sections of tau neutrino production and mu neutrino production. So essentially, is the ratio of the rates that you will produce a tau neutrino versus a mu neutrino. And so you will see that the tau neutrino is harder for it to interact to make a tau because the tau is more massive than the muon. And so in the range of most neutrino experiments that are somewhere between less than 30 GeVs, that is extremely suppressed by the heavy tau mass. In the case of IceCube, we are going to be operating in the TeV energy range, so we are way on the right of this plot where this is not a problem. So in low energy neutrino experiments, it's hard to make tau neutrinos, and additionally, it's very hard to identify them, because if you make a tau neutrino, that's going to typically, for example, if it's a 10 GeV tau, it's going to only travel about half a millimeter. So it's very hard to construct detectors that have good spatial resolution and also large volumes, so you can actually see these events. In the case of IceCube, we're going to have that the cross section is large, and additionally, the energies are large enough so that they can make large macroscopic separations. So our events are going to, and the ones I'm going to talk in this talk, are going to be extremely high energies and well above those that presently accelerator experiments use. So where are these neutrinos going to come from? Neutrinos, most of IceCube neutrinos are going to come from cosmic ray air showers. So a cosmic ray particle, so charged particles, going to hit the Earth atmosphere, it starts a cascade of particles that are producing mesons, pions, and kaons, which decay making neutrinos. Atmospheric neutrinos come from all directions. The cosmic ray flux approximately isotropically hits the Earth and yields neutrinos in all possible directions. We're going to talk in this talk about the direction of the neutrinos as an important parameter. So let me stop for a second and define what that means. So I'm going to talk about the Scenic Angle, and the Scenic Angle is 0 when it comes from the South Pole, and is pi when it comes from the Northern Hemisphere for us. So IceCube is going to see lots of these atmospheric neutrinos on the order of tens of thousands per year, depending on the purity of the event selections. This distribution may look a little strange for you. These black dots here are essentially all atmospheric neutrinos, because the atmospheric neutrino flux actually keeps growing as you go to lower energy. And the reason is that the atmospheric neutrino flux keeps growing. However, the at lower energies, the IceCube experiment is not very efficient at detecting events. And the reason is that the low energy events do not produce enough light for it to hit our very much separated detectors. So most of IceCube atmospheric neutrino events are going to be somewhere around the TeV. So IceCube is very much a TeV neutrino observatory. At high energies, we have more. We have astrophysical neutrinos, and that's what Nahi works on. And those are going to populate the high energy range. Famously, we have seen one of these neutrinos, or some of these neutrinos in coincidence with a flaring blazar known as the TXS source. And that has been, that was observed by looking at a flaring gamma ray in coincidence with a neutrino observation. So the summary of this is that we're going to be interested in looking at neutrinos changing flavors. IceCube is a high energy neutrino experiment. The center of mass energies of our experiment are comparable to the LHC, which allow us to look for very unusual things like tau neutrino interactions, which are tough. And we're going to use two neutrino sources. We're going to use atmospheric neutrinos, which are well understood, and the newly discovered astrophysical neutrinos. Okay. So now with those tools in mind, I'm going to give you 3 examples to find new friends for our neutrinos. So first, I'm going to look for a new type of neutrino. Oops. There are 2 interesting or funny things about neutrinos. One is why are neutrinos left-handed and where they're the right-handed partners. And the other one is experimental, which is going to be related to some anomalies you may have heard in the neutrino sector. So let me comment on that second point. There are 2 long-standing anomalies. First one is the Lsnd anomalous observation. So Lsnd was an experiment that operated in Los Alamos in the 90s, and it had a very pure muon antineutrino beam, and it looked for conversion of muon antineutrino to electron antineutrino. And it saw an excess of electron antineutrino events. So you can see that on the plot on the top. Those are the data points, that's expected backgrounds, and that excess of events is about almost 4 sigma in significance, and it can be interpreted as an anomalous conversion between new mu's and new me's. The bottom, this experiment was followed up by a minimum experiment at Fermilab. A minimum also made a measurement of mu neutrino to electron neutrino, and you can see the backgrounds here are these stack histograms, and the data is crosses. And you can see that again, minimum observes excess of electron neutrino-like events over the expected backgrounds. You can interpret these observations as conversion from mu neutrino to electron neutrino. And in order to fit that with the right oscillation frequency, you require a mass square difference of 1 electron volt square. So this is a problem because the mass square differences that we know, the solar one and the atmospheric one earlier that I was referring, are much smaller. So you cannot have 3 mass square differences with only 3 neutrino states. So these anomalies have been long time now for a long time. They are also being followed up by other interesting observations. So for example, there are also been some hints of things going on with electron neutrino disappearance. So those are experiments that look as they accept the questions if the electron neutrinos are the same as you would expect, or appear in the rate you would expect. One of which is the Neutrino 4 experiment in Russia. So here they measure the number of neutrinos as a function of the ratio of the length to the energy of the neutrino. And so the null hypothesis, if there is no standard oscillation, is the green line. And what they see is this oscillatory pattern that you see here with these crosses. And the significance of this is around 2.8 sigma. You can also use well understood radioactive sources to see if these neutrinos are indeed disappearing. And recently, the best experiment, also in Russia, has claimed evidence for a 5 sigma level disappearance of electron neutrinos compatible to these observations. So how do you explain these anomalies? The vanilla and the simplest solution is for them to be explained by something as a light cell neutrino. And so you need to introduce a 4 neutrino state that has associated a new neutrino mass, nu4. That mass state is comprised of mostly a stellar neutrino flavor. The stellar neutrino flavor means that it's a neutrino that does not participate in a standard model interaction. So it doesn't talk to the C boson or the W. it only appears through this oscillatory phenomenon. So the game here is to try to figure out what is the mass square difference, if it exists at all, between the new mass state and the known mass states, and to figure out how much of the new form, also of the new mass states, is of electron, muon, and tau flavors. Such a model is able to explain the observations that I pointed you earlier. These observations should be related. So mu neutrino to electron neutrino appearance, electron neutrino disappearance, and mu neutrino disappearance are related by 3 parameters. So those are going to be how much electron component does the heavy state has, how much muon component does the heavy state have, and what's the difference between the heavy state and the light state, which is the green box here. And for this model to work out, when a mu neutrino, when electron neutrino appears, the mu neutrino must disappear. So they must all go at the same frequency in the oscillatory patterns, and the amplitudes must be consistent. And that is what is somehow manifesting these equations that relates these 3 probabilities of oscillations. So if you claim that Lsnd observed the appearance of electrons in a mu neutrino beam, that implies that both UE4 and UMu4 must be non-zero, which implies that you should see disappearance of electrons, which there are some indications, and you should also see disappearance of muons, which there are no indications at the moment. So you can put all of the data that we have on that's relevant for this particular set of oscillatory patterns in a big pot, and you can stir it together and combine it and ask yourself, so at the end of the day, when I consider the constraints and I consider the signals that I'm seeing, these hints, and I put it together, what is the significance of these observations? And the answer is that the significance is extremely high. So the delta chi-square between no stellar neutrino and stellar neutrino is 52 chi-square units with 3 degrees of freedom. So the data certainly wants something that's not beyond the standard scenarios. But there is a reason we haven't claimed there's a 4 neutrino, and the reason is the following. When I take all of that data, all of the neutrino data, and I split it into 2 different data sets, I split it into appearance data sets, which are things like look for mu neutrinos compared to electron neutrinos, and data set that look for disappearance. That means like electron to electron or muon to muon. They actually point to different regions. So in these 2 plots, the mass square difference, which is again what tells you the frequency, and the mixed angle, which tells you the amplitude of these oscillations, are showing the vertical and horizontal scales. The crosses that I put here in black are in the same positions in both of these panels. And so you can see that the appearance wants large mixing, so large sine squares and small mass square differences, but the disappearance wants the opposite. They want large mass square differences and small mixings. And there is not a single point solution that's actually in common between these sets, which means that, yes, it's true, something is needed, but this doesn't seem to work because it's contradicting on itself. So in IceCube, we are going to go in a different direction to test these scenarios. So we're going to look for mu neutrino disappearance. We're going to look for a deficit of mu neutrino, which is the channel that's missing. And this is the reason why these channels do not overlap at the moment. Our neutrinos are going to be very special compared to those other experiments because our neutrinos are going to go to the whole planet when they're producing the atmosphere. So in most scenarios that look for stellar neutrinos, they operate in the scenarios where essentially they operate in vacuum, where the Hamiltonian on top works. However, for our case, because of the large matter I have to go through, the matter effects are going to be important. What do I mean by that? Is like, for example, in this diagram, you have an electron neutrino. An electron neutrino can interact with electrons, which are current scattering, or can interact with protons and neutrons via neutral currents. The other neutrino types can interact with the protons and the neutrons via these neutral current interactions. However, stellar neutrinos don't have any interactions. So when essentially when an electron becomes an electron neutrino, it doesn't feel it feels the matter effects in a different way. And this is going to depend on how it crosses to the planet, because if you cross to the core, the active neutrinos are going to feel like lots of interactions. but when you cross it in a shallower angle, you're going to see less of these effects. So how dramatic is this? This is actually quite a significant effect. So in this figure here, I show you the probability of a neutrino converting flavors. So green color is mu neutrino, and pink color is stellar neutrino. The horizontal axes are the distance, and we are going to have a neutrino that's going through the whole planet, as shown in the figure on the left. So if I have a neutrino, you can see that it like just oscillates, it converts sterile, mu, sterile, mu, sterile, mu. Nothing much exciting happening there. But if you look at the antineutrino, you'll see that the antineutrino just essentially completely converts from anti-mu to anti-nu sterile. And this is because of this matter resonance conversion, essentially. So where does this resonance conversion happens? The resonance conversion happens approximately at TeV energy, which is extremely convenient because that's where most of IceCube neutrinos actually exist. And so we can use the the broad energy distribution of IceCube to look for these effects. So how do you look for such conversion? So we're going to measure two things of these neutrinos. We're going to measure the length of the neutrino trajectory, which is going to be given by the angle in which the neutrino arrives at the detector, and we're going to measure the energy of the neutrino that arrives to us. And from those two things, we're going to extract two parameters. We're going to extract how many do they disappear, which is the mixing angle, and what is the frequency, so the mass square difference of that particular oscillations. So in these three plots in the bottom, the horizontal axis shows you the direction. So this is the cosine of the Scenic Angle. -1 means it goes to the whole planet, and 0, it comes horizontally at the detector. And the vertical axis here is the neutrino energy. And I have, for these three figures, I have fixed the mass square difference to be the same value as shown on the plot on the top right. So what you see here is the left is a small mixing angle, and as I increase the mixing angle, you can see that the disappearance, which is red means more disappearance, the disappearance increases and it moves towards from the core of the planet towards the mantle of the planet as you increases the cos theta range. So that is the signature of the stellar neutrino that we are trying to look for, this very localized disappearance signature. You will also see in this plot that the top right corner, top left corner also has some colors, which means that there is appearance. That is actually not related to stellar neutrinos at all. That is just the fact that at high energies, the Earth becomes opaque to neutrinos. And so that's unrelated to this phenomenon. Now, in the other direction, if I fix the mixing angle and I move the masses of the neutrino states, what it does, it changes the location of the resonance in energy. So for example, here is shown from large mass co-difference on left to small ones on the right. So you can see that the larger the mass co-difference is, the higher the energy where the conversion happens, and the smallest is the lower the energy where it happens. So we're going with an analysis looking for this conversion. We call this analysis meows for matter enhanced oscillation with stereos. We think it's very cute. And we use 8 years of IceCube data. And I want you to look at this plot on the top because I think this is a really, really cool thing here. So what you're seeing here is the rate or our detector normalized to some standard rates as a function of all of the years that we have seen neutrinos within IceCube. And so you can see that the rate has some periodic behavior. So this periodic behavior is because the atmosphere temperature is changing and it changes the yield of muons. This has actually been seen in muon experiments that the muon rate, of course, depends on seasons, but this is actually one of the first times we observed it with neutrinos. Of course, we correlate the signatures. But it also shows the stability of the IceCube detector throughout these many years. So this analysis uses about 300,000 mu neutrino events to search for this effect. And so the end solution is that IceCube didn't find anything significant towards stellar neutrino. We do find a preferred region at 90% confidence level. The preferred region wants a mass core difference around about 4.5 electron volt square with a relatively large mixing. This is interesting because that's in the bulk rate where the correct mass core differences should be. However, the significance is not very high. The null hypothesis is only rejected at 8% p-value. Additionally, there have been some recent results from the micromoon experiment. So micromoon is an experiment that ran in the same baseline as minimoon, and they also look for appearance of electron neutrinos. And they recently reported that they saw no significant excess. However, the limits for micromoon are not extremely strong at the present time. So takeaways from stellar neutrinos is that we can look for new particles by looking for new oscillation signatures. And IceCube results on new appearance seems to be on the bulk part of where the global solutions are, but the significance is very slow, so it's at best a hint. And with the negative observations of micromoon, the situation is just very confusing. So now let me talk about searching for new forces. So I'm going to try to look for neutrino dark matter interactions. So many experiments and people have looked for dark matter in different fashions. So one of the ways people look for dark matter is by looking for dark matter annihilation into standard model particles. How that works is you have dark matter collides with another dark matter particle, and depending on your theory, you end up producing standard model particles like WCs and whatnot. Those decay into finally stable products. And you can see those products in gamma rays, in neutrinos, or in other cosmic ray experiments. And so the game here is, I have to look for a place where I know there is lots of dark matter and look for more neutrinos than I expected. In this particular case, what we did is we look for the galactic center, and we look at a clustering of neutrinos around the galactic center as a signature of dark matter. We did not find any such clustering, so we just put a constraint. And you can do the same thing with many other experiments. This is a survey we did with Aaron Vincent, who is here at Queens, where we surveyed essentially every neutrino experiment we could think about and asked the same question, right? Are there more neutrinos than what you would expect for a given mass in the appropriate direction? And the answer is, in all over these ranges, is no. So that's not very satisfying. However, there is something that you can do that it's only possible when you see astrophysical neutrinos, and it's to think about the interactions between neutrinos and dark matter. So we believe that most of the astrophysical neutrinos are of extragalactic origin. That means they're produced by faraway sources. So to first order, you can think that the astrophysical neutrinos are coming towards the galaxy in an isotropic way, approximately. If there is an interaction between dark matter and neutrinos, the neutrinos that are going through the galactic center are going to experience more interactions with more chances to interact with dark matter than neutrinos that are coming on an orthogonal direction. And what that does is that introduces an anisotropy in the neutrino sky. So we can look for that anisotropy in our data as a signature of dark matter neutrino interactions. So this is the neutrino sky at above 60 TeVs. So these are different events here. And the crosses means cascades, and the X means tracks. There are no errors, but the errors on the cascades are quite large. The tracks are essentially order of the size of the marker. This is on galactic coordinates. So the center here is the galactic center, and the color scale is the column density of dark matter that you are going through. And so the red is where there is more dark matter. So you would expect a deficit of events around this region. And this plot, unfortunately, is really a little misleading because you do see that there are no neutrinos in the galactic center. But I promise you that if you make a statistical analysis, you'll find that this distribution of events is actually an isotropic distribution to first order. So we found no signal of these interactions at the moment. We can actually also get other handles on dark matter neutrino interactions. For example, depending on the interaction type, the energy, the region where the neutrinos interact with the dark matter is going to be different. So on the left, I have this model where you have like a scalar dark matter with a fermionic mediator. And in that case, there is this S-channel process that allows for a resonant production or resonant interaction at a given fixed energy. And what that does, it distorts entirely my distribution of events in energy, as you can see in the top left plots. So when we're looking for dark matter neutrino interactions, it's not only that we're looking for a deficit in around the galactic center, we're looking for a deficit accompanied with some kind of energy distortion that is model dependent. And with that, we can actually put constraints on the dark matter neutrino interactions, and these are shown in these plots here. I'm sorry, these plots are a little confusing. Let me talk about the one on the left. The one on the left has horizontal axis is the dark matter mass. We're all talking about relatively light dark matter. And the vertical axis is the mediator mass of this interaction. And the color scales tells you how large this coupling can be between these interaction processes. And so one way of thinking about if this is interesting or not is to think about compared to other places where you can look for these interactions. For example, you can constrain dark matter neutrino interactions by looking at large scale structure. And so I've drawn this pink line here that separates the region of parameter space where the IceCube constraints are better and the cosmological constraints are better. In this case, it turns out that for high mediator masses, IceCube is better, and for low mediator masses, cosmology is better. So on this topic, I want to summarize it as that the fact that we see high energy physical neutrinos that are going to large amount of dark matter brings us unique ways of looking for interaction with dark matter, and our analyses are essentially statistically limited. So with more data coming in, we want to improve them. Now I want to talk about the last thing here, which is related to looking for new space-time symmetries. So as I was saying in the beginning, neutrino oscillations is a phenomenon when neutrinos have essentially their own internal clock. So they know when to turn flavors. They go like mu, 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 mu. And so they have this periodic behavior. However, that if I start changing the relationship between energy and momentum of the neutrino, which means that I essentially violate Lorentz invariance, I can actually distort these internal clock that the neutrinos have. And that distortion can introduce new flavor conversions. Now, Lorentz symmetry is, of course, a building block of the standard model and of physics in general. But the idea here is that in the most fundamental theory, for example, a theory like quantum gravity, you could have Lorentz symmetry be exact, but at the lower energies, it could be spontaneously broken in a small range. So what we're going to look for here is for signature of that spontaneous Lorentz violation symmetry breaking, and I will tell you how we do that in a second. So we're going to use the flavors of physical neutrinos this time, and so I'm going to classify them in a very simple way, and hopefully it will illustrate points. So they're going to be pion sources, muon sources, and neutron sources. So pion sources, you produce a pion, decays to a muon and a mu. Muons subsequently decays. So you can count the neutrinos, you get 1 electron neutrinos and 2 muon neutrinos. So we label that as a 1, 2, 0 source. Now, if the magnetic fields are strong, that muon will synchrotron radiate, and then will no longer yield high energy muons, muon neutrinos, sorry, and you only have a new mu. So I label that as a 0, 1, 0 source. And you can have production of neutrons, and that will produce a 1, 0, 0 source. So we organize these sources in something as a flavor triangle. The flavor triangle shown here. It's a slightly confusing plot, but so let me explain it for you. The horizontal axis is the fraction of electron flavor. The right axis is the fraction of muon flavor, and the left axis is the fraction of tau flavor at the Earth. If I am at the top, I'm 100% muon neutrinos. If I'm on the right, I'm 100% electron neutrino. If I'm at the left, I'm 100% tau neutrino. And if I'm in the middle, I go in this direction to measure the fraction of electron, horizontally, fraction of nu mu, and vertically the fraction of nu tau. So every point just gives me a fraction of the 3 flavors. So given the mechanism of production, the pion, neutron, muon damp, I can use the knowledge of neutrino oscillations to actually predict the array of the flavor measurements that you will have at the Earth. And those are these colorful regions you see in this figure. And you see that most of this triangle is actually just empty and white. That means that if I measure a flavor composition that's on the white region of this triangle, I've actually discovered new physics. So that's the game that we're trying to achieve here. Unfortunately, our measurements are statistically limited. And so here is one of our latest flavor triangle measurements. And so here the measurement is in the black, not the green. And so you see that the centermost of the triangle where the standard predictions lives is allowed at 60%. And what is disfavored is the top corner and the rightmost corner. So the idea is that we're going to look for signatures of Lorentz violation via this flavor merging. And like I was saying, the idea is that Lorentz symmetry is spontaneously broken and it leaves a field through space that permeates space, much like the Higgs fields, and that field can interact essentially with the neutrinos, producing observable flavor changes. So what we are doing here is essentially a Microsoft Morley type interferometer, but interferometry is being made with neutrinos, and they're going order, extragalactic distances. So how do you observe this? So depending on, we do not know how Lorentz symmetry is broken, so we need to parameterize it in given ways. And so what we do is we parameterize it by means of effective operators. Different effective operators will produce different trajectories on these flavor triangles, depending on how I put them. So for example, if I have a Lorentz symmetry, if what remains of the Lorentz symmetry respects interacts equally with electrons and muons, you will get something like the red line, and different scenarios are different line combinations. So this is a recent paper we put on the archive late last year that shows you our constraints on Lorentz symmetry using these anomalous flavor conversions. And so the horizontal axis is the flavor composition of the source, parameterized as x1 minus x0, which means that x equals 0 means 100% nu mu, and x equal 1 means 100% nu e, and x in between means different ratios of nu e's to nu mu's. And what you can see is that there are different colors here, which tell you different effective operators that violate Lorentz invariance. But what matters here is this horizontal pink line. The horizontal pink line is when the size of the operator is of the Planck scale size. So what we have achieved here is we have built a probe, which is like this flavor conversion that has a sensitivity that is well beyond the Planck scale in some of these scenarios. So takeaway here is that IceCube astrophysical neutrinos have actually reached this Planck scale physics by doing these interferometric measurements that are extragalactic scaling sizes. And this is interesting because this is a territory where you expect quantum gravity effects to become manifest. So I hope that I have convinced you that IceCube can do lots of different sciences that is unique, and that we can discover or confirm some of the hints that we have seen in other contexts. But I want to point out that IceCube is actually expanding. We are building an improved sensor that will deploy over the next year. That will include 7 additional new strings, and those will improve the flavor identification. So the things I talked to you about today, which is differentiating different flavors, looking for the signatures, is just going to get much better. Later on, we plan to have a next upgrade, which is called IceCube Gen 2, which will build a 10 times larger detector than what we have at the current times. And that's also exciting because we will be able to see higher energy neutrinos and more neutrino sources. The IceCube is not alone in this quest for looking at the neutrino sky. There are many other alternatives. For example, P1 here in Canada, but I want to point out something that is close to my heart, which is called Tambo. Tambo is the idea to build a neutrino detector in the Andes. We will use water Cherenkov tanks to look for interactions of neutrinos on the mountains, producing charge leptons, as you can see in this cartoon on the right. And this is, I think, cool because, like I was saying earlier, tau neutrinos are the least size of the neutrino flavors, and this is a specific measurement for that. And in general, what we're going to see over the next years, my hope is that the neutrino telescopes are just going to become more precise and larger. So what you can see in the plot on the left, in the top panel, is the volume of neutrino telescope at the moment. We have like 1 cubic kilometer, but in some years, we'll actually have also Baikal GBD and KM2net operating in the Mediterranean and Russia respectively. And that will give us about 4 or 5 cubic kilometers of active volume. And then in the 2030s, we're going to have IceCube Gen 2, and hopefully we have P1 here in Canada, and other things like Tambo, which will give us further insight. So to conclude, neutrino physics is, I think, in very interesting times. We have persistent anomalies to pursue. The dark matter problem may be related to neutrinos. I've talked to here. High neutrinos seems to reach the Planck scale, and I think that the future is going to be bright, and I hope that our physics will be BSM. With that, thank you so much for listening.
Thank you very much, Carlos. And I had to apologize. I didn't introduce you properly. I was just in my sleepish mind with the 4 overlapping meeting going on right now. I thought that, of course, everyone knows Carlos, but that was absolutely my fault. So I just give me 30 seconds to reintroduce you. So Carlos, Dr. Carlos Argüelles is currently Harvard University assistant professor. He got his PhD in UW Madison. And he has a long list of fellowship and awards, and one of the things is a Sloan Research Fellow, but he has IceCube Collaboration Impact Award. If you are anywhere involved with IceCube collaboration, then you should know him, and so that was my fault. I'm sorry about that. Moving forward, sorry. Any questions? I don't see any person raising hand. So let me ask one question. So there are actually maybe 2 parts of the question. One question is, you said that the IceCube upgrade obviously is going to improve flavor measurement, but at the same time, it's going to be more focused on the lower energy end compared to high energy end, right? So for the beyond the standard models that the studies that you are doing, which part is going to be the most promising channel that will be opened by IceCube upgrade?
So yeah, IceCube upgrade will improve the low energy threshold, so that's going to be really important, but it's also going to measure the ice properties much better, and that is going to reduce the systematic uncertainty that we have on flavor identification. One thing that limits us, our capacity to, for example, reconstruct double banks, is the uncertainties in the ice model, and those are going to be reduced. So in the flavor identification, the high energy side will be improved by the ice uncertainties getting reduced. The flavor identification in the low energy side will be improved because we'll see more events and much more light. And I think that will be, I think, pretty interesting, because one thing that we haven't done yet is look at cascades for neutrino disappearance, for example, or appearance, and that will definitely benefit for better ice knowledge.
Thank you. And I see Tony raised hand. Tony?
Yeah, this might be a daft question, but when you were talking about neutrino dark matter interactions and scattering I was trying to figure out if there were areas of overdensity or underdensity at the 5 or 10% level in our galaxy, which I think would be quite reasonable. How would you distinguish an anisotropy that you see here from the fact that you have some irregular dark matter?
Yeah, that's a good question. So in some sense, this works kind of because we at the moment have not seen the galactic components of the neutrino flux. So that's a subdominant contribution at the moment. But as we make more precise measurements, we should start seeing that galactic component, and then we have to model those level 10% differences in the neutrino yield of the galaxy. So essentially what I'm saying is that the galactic component is smaller than the distortion that you get from the astrophysical neutrinos disappearing that are mostly extragalactic. Does that answer your question?
Yeah, thanks.
I see Christopher has a question.
Hi, I have a really basic question just because I don't know all that much about neutrino oscillations. On slide 54, there was, I think it was 54, yeah, these 3 figures at the bottom. These all look like they have sort of a vertical line in them at around minus 0.8. Does that have to do with the density of the core versus the mantle, or is that, am I just seeing things, or is it something else?
You have a great eyesight. That is the transition between the inner core and the mantle.
Okay, thank you.
And in fact, with high energy neutrinos, this affects the neutrino oscillations, but it also affects the transparency, which so you can see that the top corner, which is the opacity of the Earth, also has like a kink around 0.8. Mm-hmm. So you can measure the mass of the planet and the density of the planet with this procedure. And this has been done with IceCube neutrinos. You can weight the Earth essentially with only this neutrino. Mm-hmm. So yeah.
Cool, thank you.
No problem, thank you.
Okay, any other question, Tony? I assume that was a raise the hand from the previous question.
Correct.
Okay.
Sorry.
No problem. I think that's since we already passed the 1 hour mark, I think we will wrap it here. And thanks again for Carlos for brilliant talk about IceCube beyond the standard model. And thank you everyone for joining us in our first remote colloquium. And hopefully you will stay healthy until we see each other again in the beginning of March. And as usual, I would like to ask graduate students or postdoc who want to stay and then talk with Carlos. He's an excellent person to talk to, so I super encourage people to stay behind and talk with him. But meanwhile, I nicely ask other faculty members to leave the Zoom room so we can toss the button to the younger generation. And now I will end the